When we close our eyes and imagine the universe, our minds often drift first to the stars. We picture the sky filled with countless shining points, some faint, some blazing with brilliant intensity, each a sun, each perhaps the center of its own family of planets. We have been trained, almost unconsciously, to associate planets with stars, as though they must belong together, like dancers forever circling a guiding flame. It is easy to believe that this is the only way a world can exist, tethered to a sun, warmed and lit by its constant fire. Yet as astronomers have begun to peel back the veil of space with sharper instruments and more daring ideas, they have uncovered a possibility that unsettles this familiar picture. Not every planet is bound to a star. Some are alone, drifting in silence, cut adrift from the gravity that once held them close. These are the rogue planets, worlds that wander the galaxy without a sun to call their own, and their existence reshapes how we think of what it means to be a planet at all. The very idea carries with it a sense of strangeness. Imagine standing on such a world, though in truth no human has ever seen one up close. The sky above would not shift from day to night, for there would be no rising sun to mark the passage of time. Instead, there would be only the endless blackness of space, scattered with distant starlight too faint to warm. The surface, if it lay bare, would be a frozen desert, locked in cold so deep that familiar life could not endure. Yet somewhere below that frozen skin, heat might stir, the quiet exhalation of radioactive decay, the last memory of a planet's fiery birth. It is within this delicate balance, between the silence of exile and the stubborn persistence of energy, that the enigma of rogue planets takes root. To understand how such worlds come to be, we must step back into the unruly infancy of solar systems. In those early days, stars are born within clouds of dust and gas, and around them spin vast disks of matter from which planets emerge. This process is anything but orderly. Giant worlds form and tug at their neighbors, orbits overlap, and collisions scatter fragments across space. Gravity, the sculptor of the cosmos, can also be merciless, and in its relentless grip, some planets are flung away. A giant planet may sweep too close to a smaller one, ejecting it like a pebble from a sling. Or perhaps a passing star brushes near a system, its gravitational pull disturbing the fragile balance and casting worlds into the void. Once set loose, these planets do not stop. With no star to catch them, they drift onward, traveling for billions of years through interstellar darkness, never to return. What makes this vision so haunting is not merely the violence of their exile, but the sheer scale of their population. Astronomical studies using microlensing, a technique that measures how a massive body bends the light of a more distant star, suggest that rogue planets may be astonishingly common. For every star in the Milky Way, there may be one, or perhaps even several, of these wayward worlds. The galaxy could be teeming with them, hidden in the blackness between stars, invisible except in rare moments when their passage bends light just enough to reveal their presence. If true, then the universe is not merely a dance of stars and their companions, but a vast sea of lonely travelers, unseen yet countless, forming an invisible framework of planetary wanderers. To think of them in this way is to shift our understanding of what a planet can be. We tend to define worlds by their relationship to a sun, measuring their character by how far they stand from the warmth of their star, by whether they dwell in the so-called habitable zone, where liquid water might persist. But rogue planets break this rule entirely. They have no star to orbit, no habitable zone to occupy. Their potential for life, their story, must come from within, from the energies locked in their cores and the chemistry hidden beneath their shells. In this way, they become symbols of resilience, of possibility, in places we once dismissed as barren. They whisper to us that the universe may be more generous in its definition of home than we ever dared to think. Yet for all their mystery, rogue planets are not beyond our ability to imagine. We can build mental pictures from the evidence of worlds we already know. Consider the moons of Jupiter and Saturn, Europa and Enceladus, whose icy surfaces conceal oceans kept liquid not by sunlight but by internal heat. If such small moons can hold seas beneath their showers, Els, then a larger rogue planet, cast adrift, could do the same on an even grander scale. We can picture it, an ice-crusted sphere, drifting endlessly, yet below the ice an ocean stretches, vast and unlit, stirred by currents warmed by geothermal activity. Within this darkness, life could arise, Perhaps simple microbes feeding on the chemicals released by vents on the seafloor? Or perhaps something more complex, organisms shaped by conditions we have never seen? These images do not belong solely to the realm of fantasy. They are grounded in the lessons Earth has already given us, in the extremophiles that thrive in places once thought inhospitable. The thought that life could persist in such exile transforms rogue planets from curiosities into something deeper, something profound. They become not just drifting rocks, but potential cradles of biology, hidden from our sight, yet alive in ways that expand the meaning of existence. Even if no complex creatures swim in their seas, the possibility of microbial ecosystems alone suggests that life may be far more common than the narrow circle of starlight around suns would imply. Instead of life being a fragile flame requiring constant sunlight, perhaps it is a stubborn spark, able to endure in the most unlikely shelters. And if rogue planets carry such sparks, then they may also carry the seeds of life from one star system to another, crossing the galaxy in a slow migration of biology, unseen but steady. It is here that science brushes against philosophy, for rogue planets invite us to reflect on solitude and survival. They wander without guidance, without the regular rhythm of orbit, yet they endure. Their isolation mirrors the human feeling of being adrift in a vast universe, seeking meaning in the silence. Yet within their exile may lie abundance, and within their darkness may glow the hidden warmth of life. They remind us that even in what appears empty and cold, there can be persistence. There can be stories unfolding beyond sight. Detecting them remains one of astronomy's most delicate challenges. Without a star to illuminate them, they reveal themselves only through gravity's subtle fingerprint. When a rogue planet passes in front of a distant star, its mass bends and magnifies the light, creating a brief brightening that astronomers can measure. These fleeting events are rare and difficult to capture, requiring patient watching and precise instruments. But each one that is recorded adds to the evidence that such worlds are numerous, perhaps numbering in the hundreds of billions across our galaxy alone. The thought is staggering. Invisible to our eyes, yet everywhere, they drift, forming an unseen population as vast as the stars themselves. What would it be like to approach one? Imagine a spacecraft venturing far into interstellar space, guided not by a target star, but by the faint signal of a passing lensing event. The ship would close in on a world shrouded in blackness, its surface cloaked in ice. Instruments might detect the faint warmth of its interior, the possibility of liquid water below. Probes could pierce the ice, sampling what lies beneath. Perhaps they would find silence, a sterile sea, or perhaps something astonishing. Microbial mats clustered near vents, chemistry humming with the energy of life. The very act of such discovery would change how we think of biology, not as something tied to fragile conditions, but as a universal tendency, arising wherever the ingredients align. For now, these visions remain dreams, but they are dreams rooted in scientific reason. They are supported by what we know of planetary formation, of geology, of the resilience of life. They are the gentle blending of evidence and imagination, carried forward not as fanciful stories, but as serious inquiries into the possibilities of the cosmos. To drift with them in thought is to allow ourselves to feel the wonder of a universe still full of secrets, and to embrace the possibility that life's story is far larger than the circle of our own sun. And so, as we think of rogue planets, of these lonely wanderers moving in silence, we are reminded of the richness of the cosmos. We see not emptiness but abundance, not exile, but resilience. They are enigmas, yes, but also promises. Promises that the universe holds more than we can see. Promises that even in darkness there can be warmth, and in solitude, life. They are reminders that we too are wanderers in a vast night, seeking light and meaning, and that perhaps the very act of imagining them brings us closer to the truth of our own place in the cosmos. And as this thought settles, calm and steady, it allows the mind to drift, much like those planets themselves, through the dark yet comforting expanse of possibility, carrying us softly into the stillness where sleep begins. When we speak of planets adrift in the darkness, the mind naturally turns to how such loneliness begins. A world does not set out to be a wanderer. It is born in a cradle of light, in the swirling embrace of a young star's disk, surrounded by the glow of creation. To imagine the birth of a planet is to step into one of the most elegant yet tumultuous stories the cosmos has to offer, a story that unfolds slowly, over millions of years, in silence so profound that it is difficult for the human mind to grasp. And yet, from this silence come worlds, sculpted by gravity, nurtured by dust, forged by collisions both gentle and violent. Each planet is, in its earliest days, a child of chaos and chance, shaped by the invisible hands of cosmic law. Some remain bound to their star, circling it faithfully for billions of years, while others, through twists of fortune and the mercilessness of gravity, are cast out, sentenced to drift forever. To understand exile, we must first linger in the story of birth. The beginning takes place in vast clouds of gas and dust, drifting quietly between the stars. For ages, these clouds remain undisturbed, stretching across light years, cold and tenuous. But then something stirs, a shock wave from a nearby supernova, perhaps, or the subtle tug of gravity pulling clumps together. Slowly, imperceptibly at first, the cloud begins to collapse. The matter within it swirls inward, drawn to its own center. As it falls, it spins faster, flattening into a disk. At its heart, pressure builds until atoms themselves are forced to fuse, and a star is born, igniting with brilliance. Around this newborn sun, the leftovers of dust and gas remain, circling like a vast, thin halo. It is within this disk that planets begin their quiet journey into being. At first, the material is fine as smoke, tiny grains drifting in the star's gravity, but even the smallest particle are subject to the patient touch of attraction. They collide, stick, and gather, forming clumps. These clumps collide again, breaking and reforming until eventually larger bodies emerge. Over time, kilometer-sized planetesimals arise, the seeds of worlds. The process is delicate, a balance between destruction and growth, yet, over millions of years, it gives rise to protoplanets, objects massive enough for their own gravity to pull them into spheres, still raw and scarred, but recognizably worlds in the making. In this swirling nursery, countless embryos of planets jostle for space, colliding, merging, or scattering each other. It is a grand dance, choreographed by gravity, yet full of unpredictability. For some, the outcome is stability. A planet finds its place in orbit, neither too close nor too far, circling its star with regularity. Others become giants, pulling in massive envelopes of gas, forming the towering presences of their systems. But not all planets are destined for such harmony. In the crowded arena of a young solar system, chaos is always near. A slight perturbation, a close pass of a massive neighbor, can send a smaller planet careening into a new path. If the timing and trajectory align in just the wrong way, it may not settle back into orbit at all. Instead, it is flung outward, accelerated beyond the star's pull, freed into interstellar space. What began as a child of light becomes a wanderer of darkness. The violence of these exiles is staggering. Picture a world, still young, with oceans perhaps just forming, its crust cooling, its atmosphere thickening, when a gravitational encounter tears it away. A gas giant's immense pull tugs it like a sling, and suddenly it is racing outward, its bond with the star forever broken. In the blink of cosmic time, it shifts from being part of a system to being alone, its destiny rewritten. Sometimes entire groups of planets are rearranged in this way, the architecture of a solar system reshaped by a single encounter. Even stars passing near each other can trigger such expulsions, their competing gravities destabilizing the delicate balance of planetary orbits. In this cosmic turbulence, exile is not rare but common. Indeed, it may be the fate of countless worlds. Astronomers suspect that rogue planets number in the billions, perhaps even trillions, scattered across our galaxy. If so, then exile is not an exception, but an integral part of planetary evolution. Stars give birth not only to families of orderly worlds, but also to legions of wanderers. Each one carries within it the story of its chaotic youth, the record of a system that could not hold all its children. In a way, these planets are like forgotten siblings, reminders that creation is never perfect, that balance often comes at a cost. Their existence tells us that the universe is generous in forming planets, but merciless in deciding which ones may stay near the warmth of a sun. And yet, the tale of exile is not only one of loss. For a rogue planet, separation from its star is not necessarily the end of its story. Freed from the glare of sunlight, it becomes something different, a world defined by its own inner strength. Its heat no longer comes from a star but from within, from the slow release of radioactive decay and the memory of formation's heat. If it is massive enough, it may cling to a thick atmosphere, trapping warmth, protecting hidden oceans. It may carry moons with it, tiny companions that circle faithfully, even as the planet itself drifts alone. What seems like banishment may, in another light, be survival of a different kind. To imagine such a world is to place ourselves in an alien silence. There is no dawn or dusk, no seasons, no sky that shifts with the hours. The stars would shine unchanging, distant and indifferent. Yet beneath the frozen crust, currents might flow, vents might bubble, chemistry might unfold in slow, deliberate rhythms. Life, if it ever took hold, would adapt to a world without light, becoming something wholly other than what we know. The absence of a star becomes not an absence of possibility, but a canvas for new and stranger stories of existence. Scientists trace these possibilities not only through theory, but through analogs closer to home. In the icy moons of our solar system, we see examples of what a rogue planet might sustain. Europa, Enceladus, even tiny Triton, all bear evidence of oceans beneath their frozen exteriors, sustained by heat from within. If small bodies orbiting giants can harbor such seas, then surely larger independent worlds could do the same. In studying these moons, we are, in a sense, peering into the potential lives of rogue planets, learning how warmth and water might persist even in eternal night. The notion of exile also carries a poetic resonance for us. As human beings, we are bound to a star, dependent on its warmth and its light, and so we instinctively see separation as loss. Yet rogue planets remind us that survival does not always follow the patterns we know. A planet cast into darkness may not wither. It may adapt, transforming its isolation into a different kind of home. This challenges our assumptions about where life may exist and what conditions are necessary for it to flourish. It asks us to reconsider the very meaning of habitability, to expand our imagination beyond the circle of light and into the quiet reaches of the void. There is also the mystery of how long such worlds can endure. Drifting between stars, they are untouched by the cycles of stellar death, unscarred by supernovae, immune to the swelling and collapse of a host star. They may persist for billions of years, their interiors cooling slowly, their oceans sealed away beneath protective shells. In this sense, they are not fragile but enduring, some of the longest-lasting havens the galaxy may know. If life ever begins within them, it could have eons to evolve, shielded from the violent events that punctuate the lives of stars. In their exile, they may find a kind of stability that bound planets cannot match. And so, the birth of planets, with all its chaos and collisions, leads naturally to exile, and exile itself opens the door to new forms of endurance. The story is not linear, but cyclical, with creation and scattering bound together. Rogue planets are born of the same processes that shape all others, yet their paths diverge in dramatic ways. They remind us that the universe is not a place of perfect harmony, but of ceaseless change, where even worlds can be uprooted and cast adrift. Yet in that uprooting, there may be hidden potential, hidden wonders waiting to be discovered. We reflect on these wandering planets, it is hard not to feel a quiet awe. Somewhere in the darkness between stars, a world might be drifting now, unseen, carrying seas beneath ice, carrying perhaps the faint stirrings of life. It is moving without destination, following a trajectory set long ago in the chaos of its birth. It does not know exile as tragedy, for it simply is, continuing its journey with patience beyond our comprehension. Its story is vast, unfolding in silence, yet its very existence whispers to us of the richness of the cosmos. And as we imagine it, slowly, gently, we allow our own thoughts to drift alongside, floating in the stillness, embracing the calm of the dark, as though we too were carried into the soft and endless night of interstellar space. When we last drifted through the thought of wandering planets, it was their birth and exile that filled our imagination, the way they were cast away from their stars and left to travel alone in silence. It may seem that such a fate would leave them lifeless, frozen solid in the eternal cold, their potential snuffed out the moment they lost their sun. After all, on Earth we are so dependent on the warmth of our star that it feels inseparable from the idea of life itself. Our days are governed by its rising and setting, our climates shaped by its constant energy. It is natural, then, to assume that a world without a sun must be a dead one. But here is where the story deepens and the mystery grows more compelling. For even in the absence of starlight, a planet may carry its own quiet fire, sources of heat that linger unseen, sustaining possibilities that at first seem impossible. To step into this thought is to enter a gentler kind of wonder, where warmth is not a blazing light, but a patient glow hidden beneath the surface, and where life may yet find shelter in places no sunlight can reach. The first of these hidden sources lies deep within the hearts of planets themselves. When worlds form from swirling dust and gas, the process is anything but cold. Collisions of countless fragments release immense energy, heating the growing planet until it is molten throughout. Over time, much of this initial heat radiates away into space, but not all of it is lost. Some remains trapped in the core, locked away like embers buried under ash. This primordial heat cools only slowly, over billions of years, and while it may not be enough to keep an entire surface warm, it can sustain internal reservoirs of energy. For a rogue planet, drifting alone without a sun, these lingering embers could be the first line of defense against the deep freeze of space. But there is another, more constant fire, the steady decay of radioactive elements. Within the rocks of planets lie atoms such as uranium, thorium, and potassium, unstable in their nature, slowly breaking apart and releasing heat. On Earth, this radioactive decay contributes a large share of the warmth that drives the churning of the mantle and the motion of the tectonic plates. On a rogue planet, this decay could mean survival, providing a continuous trickle of energy that, though quiet, might be enough to keep water from freezing in the deepest places. This kind of heat is not dramatic, not explosive, but patient and enduring, the kind of warmth that persists across eons. In the silent drift of interstellar space, such patience may be the key to endurance. We can look again to the icy moons of our solar system for evidence. Europa and Enceladus, though tiny compared to Earth, remain geologically active. Geysers spurt water into space, cracks open and close across icy shells, and beneath those shells lie oceans kept liquid by internal heating. Much of their warmth comes from tidal forces, the constant squeezing and stretching caused by their orbits around giant planets. A rogue planet, of course, has no massive neighbor to pull at it in the same way. Yet, even without tides, radioactive decay and residual heat can accomplish something similar on larger scales. If small moons can sustain oceans with only partial energy sources, then surely larger planets, with thicker mantles and stronger gravitational binding, could carry far more. Instead of shallow seas under ice, they might host entire global oceans, hidden worlds kept alive by heat that never sees the light of a star. Imagine such a world. On the surface, there is silence and ice, an endless desert of frozen crust, locked in darkness so complete that even the distant starlight above cannot cast a shadow. Yet deep below, there is movement. The core remains warm, its radioactive heart glowing faintly. Heat seeps upward, melting pockets of water beneath the ice. Over time, these pockets link together, forming seas and then oceans, stretching across the entire globe. The ice above forms a lid, kilometers thick, protecting the water from space's killing cold. Within those oceans, life may stir, not nourished by sunlight, but by heat and chemistry. Hydrothermal vents may dot the ocean floor, releasing hot, mineral-rich water into the surrounding sea, creating oases where life could thrive. This picture, drawn not from fantasy, but from analogs on Earth and from the science of planetary formation, is one of the most tantalizing ideas in modern astronomy, that entire ecosystems could exist in perpetual darkness, warmed by the planet itself. This brings us to the question of how life sustains itself without sunlight. On Earth, photosynthesis dominates, with plants capturing the sun's energy and passing it along the food chain. Yet life does not always need light. In the deepest oceans, far from the reach of the sun, ecosystems thrive around hydrothermal vents. These creatures do not rely on photosynthesis, but on chemosynthesis, using chemicals like hydrogen sulfide to generate energy. Giant tube worms, shrimp, and countless microbes live in these shadowed realms, proving that life can flourish without any connection to the sun. It is not a stretch, then, to imagine similar processes unfolding on a rogue planet. With internal heat creating vents and chemical gradients, chemosynthesis could provide the foundation for ecosystems, alien in form, yet familiar in principle. Here, the heat from within becomes the equivalent of sunlight, a driver of biological possibility. But geothermal heat and radioactive decay are not the only sources of warmth such a planet might hold. There is also the possibility of a thick, insulating atmosphere. If a rogue planet retains a dense blanket of hydrogen, perhaps captured in its early formation, that atmosphere could trap heat, much as a greenhouse traps warmth on Earth. Though the planet receives no sunlight, its internal energy could remain bottled beneath the atmospheric layer, creating a world that, while dark, is not entirely frozen. Some models suggest that on such a planet, surface temperatures could remain above freezing, allowing lakes or even oceans of liquid water to exist openly under starlight. These would be strange seas, illuminated not by sunlight, but perhaps by the faint glow of geothermal activity or the chemical interactions of the atmosphere itself. It is a reminder that even in exile, nature can find ways to adapt, ways to preserve warmth in the most unexpected places. One of the most fascinating aspects of this possibility is its timescale. Stars burn through their fuel and eventually die, some collapsing into white dwarfs, others exploding in supernovae. Planets bound to such stars share their fate, losing their light and heat when their star fades. Rogue planets, however, are independent. Their warmth comes from within, and so long as radioactive decay continues, so long as their cores remain even slightly molten, they can persist. This could mean billions upon billions of years of slow, steady heat, far longer than many stars remain stable. If life arises within such a planet's oceans, it may have more time to evolve and adapt than life on any star-bound world. In this way, exile may not be a death sentence, but a doorway to longevity. When scientists think about these possibilities, they often draw comparisons to the extremophiles on Earth, creatures that thrive in conditions we once thought impossible. Microbes that survive in boiling acid, bacteria that endure crushing pressures beneath the ocean, organisms that lie dormant in ice for centuries and awaken when thawed. Each one demonstrates life's astonishing resilience. If life can find ways to endure in such extremes here, it is not unreasonable to imagine it doing so elsewhere, guided by similar principles but adapted to alien chemistries. In this sense, the hidden warmth of rogue planets becomes more than just an abstract idea. It becomes a real possibility, grounded in what we already know of biology and geology. And so the story of rogue planets deepens. They are not merely cold exiles, lost to the void. They are worlds carrying secrets, warmth hidden beneath their surfaces, reservoirs of energy that defy the silence of space. To reflect on this is to feel a shift in perspective, to realize that the absence of a sun does not mean the absence of life. Instead, it opens the door to new and stranger ways of being, where heat comes not from the sky, but from the heart of the world itself. It is easy, when picturing these things, to let the imagination drift further, to wonder what creatures might exist in such darkness. Perhaps they would have no eyes, for light is irrelevant. Perhaps they would sense heat, or vibrations, or chemical gradients instead. Perhaps their lives would be slow, measured in rhythms of geothermal cycles rather than the rising and setting of a sun. To us, they would seem alien beyond recognition, yet to themselves, they would be perfectly at home, adapted to the only environment they have ever known. This thought is both humbling and wondrous, a reminder that life is not bound to our definitions, but to the possibilities the universe allows. As we let these ideas settle, we return to the feeling that the cosmos is richer than we can easily grasp. Rogue planets with their hidden fires expand our vision of habitability, showing us that life may not be confined to the narrow band around stars. Instead, it may be scattered everywhere, tucked into niches where energy still flows, however faintly. Heat without a sun may sound like a contradiction, yet it is precisely this contradiction that makes the universe so full of wonder. And so, as we drift through thought, we can picture these lonely worlds sailing silently through interstellar space, each carrying within it the quiet glow of its core, each perhaps hiding oceans warmed by fires that never see the light of day. They are not empty. They are not cold corpses. They are enigmas, keepers of secrets, reminders that even in the darkest places, warmth endures. And in this gentle realization, our own thoughts begin to quiet, our breathing slows, and we find ourselves soothed by the vastness of possibility, ready to drift into rest, carried softly as though upon the hidden seas of a world without a sun. When we last lingered with the thought of rogue planets, we imagined them holding quiet warmth within, a hidden glow from radioactive decay, from ancient heat lingering in their cores, and perhaps from atmospheres thick enough to keep their secrets. That warmth, however faint, leads naturally to the next question. If such heat can endure across the vast silence of interstellar exile, where does it go, and what might it shape? The answer, whispered softly through the lens of both science and imagination, is that it seeps into water, into the vast reservoirs that lie not upon the surface, but below it. Beneath the crust of ice and rock, hidden from the gaze of distant stars, lie oceans, entire worlds of water held close by gravity and kept liquid by warmth. They are unseen seas, stretching in silence, where life, if it comes, must learn to survive without light, guided instead by the quiet chemistry of survival. On Earth, the presence of oceans is tied so closely to sunlight that it is difficult to separate the two in our imagination. We see shimmering waves under the glow of the sun, feel the warmth of its light on the surface of seas, and understand the intricate cycle of evaporation, rainfall, and rivers that feed them. But when we turn to the hidden places of our own planet, a new story begins. Deep beneath Antarctica, under kilometers of ice, lakes remain liquid, isolated from the surface for millions of years. In the depths of Earth's crust, water flows in pores and fractures, heated by the slow decay of the rocks themselves. And beneath the ocean floor, microbes survive in darkness, living on the faint trickle of energy from chemical reactions. If it is true here, it may be true elsewhere. And if it can happen beneath the ice of Earth, then it may also happen beneath the crust of rogue planets, where subterranean oceans could stretch vast and silent, hidden world. Mars untouched by starlight. To picture one of these oceans, imagine a planet adrift in the darkness of space. From the outside, it appears frozen, its surface crusted with ice kilometers thick. The cold of the cosmos has locked the exterior into stillness. But beneath that frozen shell, heat rises slowly from the planet's heart. It is not a roaring flame, but a patient warmth, radiating upward through rock and ice, enough to melt water trapped below. Over time, what begins as pockets of liquid may merge into layers, and those layers into oceans, stretching vast and global beneath the frozen lid. It is as though the planet wears a cloak of ice, beneath which lies a hidden sea. On Earth, we know of Europa and Enceladus, moons where such oceans are believed to exist. If small moons circling Jupiter and Saturn can hold them, then rogue planets, far larger and with stronger gravity, could hold oceans of unimaginable size, their depths greater than anything we know. In these oceans, the chemistry of survival takes on a central role. Without sunlight, photosynthesis cannot serve as the foundation of life. Instead, it is chemistry itself that must provide the spark, and the universe, in its quiet abundance, has supplied the tools. When water interacts with rock at high temperatures, reactions occur that release hydrogen, methane, and other simple molecules. On Earth, such processes create hydrothermal vents, fissures on the ocean floor where hot, mineral-rich water pours into the sea. Around these vents, life thrives without the faintest touch of sunlight. Microbes feed on the chemicals, forming the base of ecosystems that rise into forests of tube worms, colonies of mussels, swarms of shrimp. It is a world powered not by the sun, but by the chemistry of rocks and water, by the patient interaction of minerals and heat. On a rogue planet, similar processes could unfold. The ocean floor, warmed from below, may host hydrothermal vents, places where hot water gushes forth, and brings with it a banquet of minerals. In such a place, life could emerge, small at first, perhaps microbial, but diverse in form and metabolism. Each chemical gradient, each difference in energy between one molecule and another, becomes an opportunity, a tiny foothold for survival. The chemistry of survival is, in its essence, the art of harnessing these gradients. Where energy flows, however faintly, life may learn to gather it, to turn it into growth, reproduction, and persistence. This is the gentle miracle of existence, and in the hidden seas of rogue planets, it may be repeating itself in silence. One of the most intriguing aspects of these subterranean oceans is their isolation. On Earth, oceans are connected to the surface, influenced by climate, atmosphere, and the cycle of seasons. In contrast, a subterranean ocean is sealed away, its lid of ice shielding it from the cosmos. What emerges within it is shaped almost entirely by internal forces, geothermal heat, chemical reactions, and the slow churn of convection beneath the crust. Such an environment is not only stable, but astonishingly long-lived. With no seasons, no sunlight, no storms or winds, these oceans may remain steady for billions of years, offering life a quiet and unbroken continuity. This isolation, paradoxically, may be a gift. Evolution, in its slow and patient way, thrives where time is abundant and conditions endure. The chemistry of survival in such oceans would be both familiar and strange. Familiar because the principles of energy, molecules, and reactions are universal. Strange because without sunlight, without photosynthesis, and without oxygen in abundance, life would follow different pathways. Instead of relying on carbon dioxide and light, organisms might depend on methane, hydrogen, or sulfur. Instead of oxygen, they might use other electron acceptors, drawing on the richness of chemistry to build metabolisms unlike anything on Earth. To us, such organisms would seem alien, yet to themselves, they would be perfectly adapted, as natural in their world as trees and fish are in ours. The chemistry of survival, it seems, is endlessly inventive, finding ways to turn even the most modest flows of energy into the spark of life. As we think of these hidden seas, it is helpful to return to the extremophiles of Earth, for they are our best guides to what might be possible. In the deep ocean trenches, microbes survive under pressures that would crush human vessels. Near hydrothermal vents, organisms live at temperatures that would cook most known life. In the Antarctic lakes sealed beneath ice, microbes persist in waters cut off from the surface for millions of years. Even in rocks buried kilometers below the crust, life endures, nourished by the faintest trickle of chemical reactions. Each of these examples shows us that life is not fragile, not limited to the narrow strip of conditions we once imagined. Instead, it is adaptable, flexible, and astonishingly resourceful. If life on Earth can endure such extremes, then life in subterranean oceans of rogue planets may be not only possible, but abundant. The thought of such abundance leads naturally to the imagination of ecosystems. Picture, if you will, the floor of a hidden ocean beneath a rogue planet's ice. From fissures in the crust, hot water pours into the sea, carrying minerals. Around these vents, colonies of microbes cluster, feeding on the chemistry. Larger organisms, perhaps analogues to tube worms or other simple creatures, gather around, feeding on the microbes. Predators may evolve, sensing vibrations or chemical trails rather than light, hunting silently in the dark. The ocean, though sealed from the stars, becomes alive with movement, cycles of energy, and the slow unfolding of evolution. It is a world entirely apart from ours, yet governed by the same laws of physics and chemistry, and guided by the same resilience of life. One might ask, how do we know such oceans could exist? The answer lies in a combination of observation and theory. In our solar system, icy moons have already shown us the way. Europa, with its fractured ice surface, say, hints at an ocean below. Enceladus, with its plumes of water vapor spraying into space, confirms it. Ganymede and Callisto, too, are suspected to harbor deep oceans beneath their crusts. If these moons, orbiting distant giants, can hold such secrets, then rogue planets, larger and more massive, could do the same on grander scales. The physics of heat transfer, the chemistry of water and rock, and the evidence we already have all point toward the possibility. It is not a certainty, but a doorway, a path of thought that invites us to see beyond the narrow boundaries of Earth. Perhaps the most profound aspect of subterranean oceans is what they reveal about the universe itself. They show us that habitability is not limited to the thin layer of sunlight around stars. They reveal that water, the solvent of life, may be common in forms we had not imagined. And they suggest that life, if it exists, may be hidden more often than exposed, living not on surfaces but beneath them, in oceans sealed away from view. This reframes the search for life, turning our gaze not just to Earth-like planets orbiting stars, but also to the countless rogues drifting unseen, each potentially carrying oceans within. And so, the thought of subterranean oceans becomes not just a scientific speculation, but a meditation on resilience. In the darkest places, warmth endures. In the coldest depths, water flows. In the absence of light, chemistry still offers the spark of survival. To imagine these oceans is to be reminded that life does not ask for comfort, only for possibility. It will take whatever is given, heat from the core, minerals from the rocks, water from the crust, and turn it into something that endures. As we let these images drift through the mind, we return to the gentle rhythm of the cosmos. Rogue planets sail silently through the void, unseen and uncounted. Beneath their icy shells, oceans whisper against rock, currents flow in darkness, and perhaps, just perhaps, life stirs. It is a life not bound to stars, not dependent on light, but born of chemistry and patience. A life that, if it exists, reminds us that the universe is vast, not only in its spaces, but in its possibilities. And with this realization, our own thoughts quiet, drifting softly into the rhythm of those hidden seas, where survival is not loud, but enduring, not bright, but steady, carrying us gently into rest, like a tide that has no shore. When we last lingered in thought, we found ourselves drifting through the silent, hidden oceans of rogue planets, imagining seas buried beneath ice, warmed not by the sun, but by the patient glow of their cores. These subterranean oceans were not empty, but filled with potential, with the chemistry of survival quietly unfolding in the dark. And as we let our minds drift further into those waters, we come now to the places where heat and chemistry come together most powerfully, to the hydrothermal vents that may lie along the floors of these oceans. It is here, in fissures where hot water bursts into the cold, that the role of survival takes on a vivid and unexpected form, a story written not in sunlight, but in minerals and heat. On Earth, hydrothermal vents are among the most extraordinary environments ever discovered. Far from the surface, in the abyssal depths of the oceans, where no sunlight penetrates and pressures grow immense, these vents create islands of abundance. Cracks in the Earth's crust allow seawater to seep deep down, where it meets magma-heated rock. The water becomes superheated, charged with minerals, and rises back into the ocean, creating jets of shimmering liquid that tower like chimneys. Around these vents, life flourishes, not just microbes, but entire ecosystems, thriving in total darkness. It is a reminder that life is not bound to sunlight alone, but can grow wherever energy and chemistry are found. To think of hydrothermal vents on rogue planets is to extend this lesson outward into the quiet vastness of interstellar space. Beneath ice and rock, along the hidden ocean floors of these wandering worlds, vents may erupt in much the same way. Heat from the planet's core drives convection, water circulates deep into the crust, and when it returns, it carries with it the richness of minerals. In the absence of starlight, these vents become lightho, uses of energy, not visible to the eye, but glowing in chemical possibility. Around them, life might find not only survival, but abundance, building intricate webs of existence in worlds that, from the outside, appear frozen and lifeless. The role of hydrothermal vents in such a setting is profound. They are not just sources of heat, they are engines of transformation. The hot water they release is rich in compounds like hydrogen sulfide, methane, and other reduced chemicals. For microbes adapted to these environments, these chemicals are food, raw energy to be harvested through chemosynthesis. Just as plants on Earth use sunlight to turn carbon dioxide into sugars, these microbes use chemical energy to build life's molecules. Around them, higher forms of life can gather, feeding on the microbes or on each other, forming food chains that mirror those on Earth, but with an entirely different foundation. Instead of sunlight, the energy begins in the chemistry of rock and water, in the hidden power of hydrothermal vents. To drift in thought through one of these oceans is to imagine a scene of quiet yet bustling vitality. Along the dark seafloor, fissures open, and plumes of mineral-rich water surge into the surrounding cold. The water shimmers with heat, creating a faint glow not of light but of energy potential. Around the vent's mouth, microbes cling to surfaces, forming mats that thrive on the chemicals rushing out. Larger organisms may graze upon them, simple creatures adapted to the darkness, perhaps sensing their environment through vibrations or chemical trails. Predators may lurk in the shadows, moving slowly in the dense waters, hunting by touch or subtle detection. It is an alien world, yet one that follows familiar rules. Energy flows, life adapts, and ecosystems emerge from the interplay of chemistry and biology. On Earth, scientists have long wondered whether life itself may have begun around hydrothermal vents. The conditions they provide are remarkable. They offer energy in abundance, shelter in the form of mineral structures, and gradients of temperature and chemistry that allow complex reactions to unfold. Tiny pores within vent structures may have served as natural laboratories, concentrating molecules, catalyzing reactions, and giving rise to the first forms of metabolism. If this is true, then hydrothermal vents are not just places where life survives, they are places where life begins. And if they could have played this role on Earth, then why not on rogue planets too? In their hidden oceans, warmed from below, vents could offer the same opportunities, seeding life in places where no sunlight has ever shone. The more one reflects on this, the more the role of vents becomes clear. They are not just features of geology, they are bridges between the physical and the biological, turning heat and minerals into the foundations of ecosystems. In the silence of a rogue planet's ocean, this role would be magnified. With no other source of energy, vents would become the central hubs of life, oases in the darkness. Entire biospheres might orbit around them, spreading outward into the ocean, but always tied in some way to the chemical riches of the vents. They would be both hearth and heart, the vital centers around which the story of survival unfolds. It is humbling to realize that the universe may hold countless such places. Each rogue planet, wandering unseen through interstellar space, could hide oceans beneath ice. Each of those oceans could host vents along its floor, and each vent could be a seed of life, a place where chemistry and biology meet. The number of such possibilities becomes staggering, far greater than the number of planets bathed in starlight. It suggests that life may not be rare but abundant, not bound to stars but scattered everywhere, hidden in the dark, gathering around vents in oceans we cannot see. As we let this possibility sink in, it invites a softer reflection. Hydrothermal vents remind us that life is adaptable, inventive, and deeply resilient. It does not need the comforts we once thought essential. It asks only for energy and a way to use it, and vents provide that in abundance. In their plumes of heat and minerals, in their gradients of temperature and chemistry, life finds opportunity. In the stillness of interstellar space, in oceans sealed beneath ice, these opportunities may be unfolding even now, quietly, invisibly, beyond our reach but not beyond possibility. And so, we find ourselves imagining again, letting the mind drift across the seafloor of a hidden world. There is no light, no sky, no horizon, only the endless dark of the ocean. Yet here, a vent rises, its chimney of minerals growing taller as water gushes through. Around it, life gathers, not in bright colors, but in forms suited to the dark, each one part of an ecosystem that owes everything to the vent's energy. The water is alive with chemistry, and the chemistry is alive with possibility. It is a scene that is both alien and strangely familiar, for it tells us something about the universality of life's struggle and the creativity of survival. To rest with these thoughts is to sense the quiet grandeur of the cosmos. The role of hydrothermal vents is not limited to Earth, nor even to the few icy moons we have glimpsed. It extends outward, to the rogue planets that wander unseen, each carrying oceans, each perhaps carrying life. In this way, vents become symbols of resilience, of life's ability to endure where no sun shines, where no star warms. They are reminders that even in the deepest darkness, energy flows, and where energy flows, life may follow. As our thoughts soften and slow, we can let the image of these vents fade gently into the background, leaving us with a sense of wonder and peace. For in the end, the story of hydrothermal vents is the story of possibility itself, a story that whispers that the universe is not barren, but rich, not silent, but filled with hidden songs of survival. It is a story that, like the plumes of the vents, rises upward into the vastness, carrying with it the gentle realization that life, in all its forms, is more enduring and more widespread than we have ever dared to dream. And with that realization, we can allow ourselves to rest, carried softly into the rhythm of the hidden seas, soothed by the knowledge that even in the darkest places, warmth and life may quietly endure. Let us imagine ourselves once again in the company of those mysterious and wandering worlds, adrift in the deep cosmic sea. We have traveled with them through their birth, their exile, their hidden reservoirs of heat, and even into their secret oceans, where the chemistry of life could stir in the darkness. We have lingered near their hydrothermal vents, where energy rises like ghostly whispers from within, fueling possibilities that remind us of Earth's own deep-sea mysteries. Now, as we continue this slow and thoughtful journey, our attention shifts to the very air, or what might take its place around these isolated spheres. We begin to wonder, in the absence of a star to shine upon them, could rogue planets cloak themselves in protective blankets of gas thick enough to keep them warm against the unforgiving chill of space? When we think of an atmosphere, we tend to picture Earth's own, a familiar blend of nitrogen, oxygen, and other gases, gently enveloping our planet like an invisible ocean. It is this atmosphere that shields us from harmful radiation, keeps our surface temperature within habitable bounds, and carries the breezes, clouds, and rains that shape our world. Without it, our planet would be barren, its warmth stripped away by the void. But on a rogue planet, floating far from the life-giving energy of a star, the challenge of holding on to an atmosphere becomes even greater. There is no steady sunlight to maintain surface temperatures. There is no gentle balance of incoming and outgoing energy to stabilize the climate. Instead, the atmosphere itself must take on a different and perhaps more desperate role, working not as a partner to a star, but as a solitary guardian, trapping the faint heat from within the planet and wrapping it tight against the cold. It is here that we encounter the fascinating physics of greenhouse gases and pressure. On Earth, we are familiar with the greenhouse effect. Sunlight passes through our atmosphere, warms the ground, and in return, the ground radiates heat back as infrared energy. Greenhouse gases like carbon dioxide and methane absorb some of this infrared radiation, preventing it from escaping into space, thereby keeping the surface warmer than it otherwise would be. On a rogue planet, however, there is no sunlight to drive this process. Instead, the tiny trickle of geothermal heat rising from the interior might be enough to initiate a similar effect if the atmosphere were dense enough to capture it. Imagine a world cloaked not in a thin veil of air, but in a heavy, smothering shroud, perhaps hundreds or even thousands of times thicker than Earth's atmosphere. Within such a blanket, the geothermal warmth leaking out from the planet's core could linger and circulate, creating a habitable environment at least below the surface or within certain protected regions. The idea may sound fantastical, but research into such possibilities has grown steadily in recent years. Astrophysicists have suggested that rogue planets might retain thick hydrogen envelopes, remnants of their birth in the swirling nebulae of early star systems. Hydrogen, though the simplest of gases, has an extraordinary capacity to trap heat when present in great quantities. A rogue planet swaddled in a hydrogen-rich atmosphere could keep its surface surprisingly warm, perhaps even above the freezing point of water, despite drifting alone through interstellar night. In this sense, hydrogen becomes more than just a building block of stars. It becomes a silent guardian of warmth, holding back the eternal frost that otherwise dominates deep space. To picture this, let us drift in imagination to the surface of such a world. The sky would not be blue, but perhaps hazy, dense, and muted, its light dim and filtered since no sun shines above. The ground might feel heavy underfoot due to the sheer weight of the atmosphere pressing downward. Breathing such air, if it were even possible for creatures like us, would feel oppressive, yet within it lies a paradoxical gift: warmth. Water could pool as liquid seas, sheltered beneath the heavy blanket of gas. Winds could move sluggishly, burdened by the weight of the air, but still carrying whispers of circulation that transport heat across the planet. In this strange equilibrium, life could carve out its existence, not in the bright sunshine we know, but in the hushed twilight of pressure and persistence. This possibility also ties back to what we know of worlds within our own solar system. Consider Titan, Saturn's largest moon, with its thick nitrogen atmosphere and seas of liquid methane. Though far from the sun, Titan demonstrates that a dense atmosphere can sustain complex surface chemistry and dynamic weather cycles even in extreme cold. Or think of Venus, where a runaway greenhouse effect has created surface conditions so hot that lead would melt. While these examples represent extremes, Titan's frigid lakes and Venus's suffocating heat, they remind us that atmospheres can profoundly shape the fate of a world. For rogue planets, the right composition and thickness could tip the balance between frozen desolation and a pocket of warmth where chemistry and perhaps biology could take root. Scientists studying exoplanets, worlds orbiting distant stars, have also sharpened their models of atmospheric retention. They ask, how long can a planet hold onto its gases before they drift into space? For Earth, gravity and magnetic fields help retain our atmosphere. For a rogue planet, without the stripping effect of a nearby star's radiation, it may be easier in some ways to keep its air. Drifting in darkness, there is no stellar wind constantly battering and eroding the upper layers of gas. If the planet is massive enough, with gravity strong enough to grip its atmosphere tightly, it could preserve that thick blanket for billions of years, maintaining its quiet reservoir of warmth through cosmic time. In such conditions, life could emerge in forms unfamiliar to us. Without sunlight, photosynthesis as we know it would not drive ecosystems. Instead, life might rely on chemical energy, drawing sustenance from the interaction of gases, minerals, and heat. Methane-based metabolisms, or organisms adapted to high-pressure environments, might thrive in niches beyond our current imagination. The atmosphere itself might become a medium for life, not just a protective cover, but a habitat where microscopic beings drift on invisible currents, feeding on chemical gradients or tiny droplets suspended in the dense air. Just as Earth's atmosphere teems with microbial life carried by winds and clouds, so too could the skies of a rogue planet harbor unseen populations, forming part of an ecosystem that survives in complete absence of starlight. There is a quiet wonder in imagining these invisible possibilities, not as wild fantasies but as extensions of principles we already observe. Every discovery on Earth of microbes surviving in boiling springs, under crushing pressures at the ocean floor, or within acidic pools expands our sense of what life can endure. Each example tells us that the absence of sunlight is not the absence of possibility. On rogue planets, atmospheres may be the stage upon which these possibilities unfold, a reminder that warmth and shelter can take many shapes in the universe. As we drift deeper into thought, we might also consider the role such worlds could play in the grander story of life across the galaxy. If rogue planets can indeed maintain habitable conditions through thick, insulating atmospheres, then they may number among the hidden sanctuaries where life takes root in unlikely places. Unlike worlds bound to stars, which we can sometimes glimpse as they pass across their suns, rogue planets are exceedingly difficult to detect. Their darkness hides them from easy view, making them cosmic secrets traveling silently between the stars. Yet their very abundance, formed and flung outward by the billions, suggests that they could be among the most common havens for life. They are like wandering arks, carrying the possibility of biology through the endless ocean of space, sustained not by the warmth of starlight, but by the determination of matter itself to hold on to heat. And so, we find ourselves returning to the question at the heart of this gentle exploration. Can thick blankets of gas truly keep warmth alive on a planet without a sun? The science tells us yes, in principle, through the quiet work of pressure, greenhouse effects, and the persistence of geothermal energy. The imagination tells us more, weaving pictures of alien skies, dense air, and strange ecosystems suspended within in atmospheric layers. And the heart, as it drifts towards sleep, takes comfort in the idea that warmth can be found even in the darkest reaches of the cosmos. From hydrothermal vents deep within oceans to atmospheres swollen with protective gases, rogue planets seem to whisper the same message, that life, or at least the conditions for it, might emerge in places where we least expect it. As our minds settle in the hush of night, we are left with a sense of continuity, that even in exile, even in eternal darkness, there are ways for warmth to endure, and for the fragile spark of possibility to be sheltered against the void. In this way, the story of atmospheres in isolation becomes not just a lesson in planetary science, but a soft reminder of resilience, a lullaby sung by the cosmos itself, carrying us gently into dreams of worlds unseen. In the stillness of our journey through the hidden worlds adrift in the cosmic ocean, we have already lingered upon many layers of their mystery. We have seen how they are born and cast away, how their interiors keep quiet reservoirs of heat, how subterranean oceans might cradle the chemistry of survival, how hydrothermal vents rise like ancient storytellers from the abyss, and how thick blankets of gas might serve as guardians of warmth in the absence of a star. Now, from these foundations, our thoughts drift naturally into the most delicate and wondrous possibility of all, the existence of life itself, not as we know it in the bright embrace of sunlight, but as something wholly exotic, shaped in the shadows of perpetual night. It is here that the imagination must walk hand in hand with science, for no telescope has yet captured a glimpse of a living thing upon a rogue planet. Yet science does not demand only direct sight. It allows us to build bridges of understanding from what is known to what may be. On Earth, life has shown an astonishing ability to adapt, to find a foothold in places where light never shines and conditions seem too hostile for survival. In the deep oceans, thousands of meters below the surface where no sunlight penetrates, ecosystems thrive around hydrothermal vents. Strange creatures, from ghostly shrimp to pale crabs and tube worms taller than a person, live in abundance, nourished not by the sun's energy but by chemical reactions. They demonstrate to us that sunlight is not the only path to life. Energy, in its many forms, can be harnessed wherever it is found. If this is possible here, within the embrace of our own world, why not also upon planets that drift forever in darkness, sustained by heat from within and the chemistry of their isolated atmospheres? To imagine the life forms of rogue planets is to step into a realm where familiar rules are reshaped, where bodies and behaviors are molded not by cycles of day and night, but by the constancy of shadow. Without sunlight, vision as we know it may serve little purpose. Eyes, if they exist at all, might be vestigial or repurposed to sense faint glows of geothermal activity. Instead, other senses might flourish: heightened perception of vibrations traveling through liquid, exquisite sensitivity to changes in pressure, or even the ability to detect chemical gradients in the surrounding environment. Life in perpetual night might be blind, but it would not be senseless. It would listen to the whispers of its world through other means. On Earth, microbes already thrive in such conditions. In caves sealed off from the surface for millions of years, tiny bacteria feed on minerals or generate energy through chemical processes. In subglacial lakes buried beneath Antarctica's ice, isolated microbial communities persist in complete darkness, their survival dependent on nutrients leached from rocks and the subtle warmth of geothermal heat. These examples hint that life need not depend upon the light of a star at all. On a rogue planet, entire ecosystems could evolve in similar ways, beginning with microorganisms that harness chemical energy, slowly branching into more complex forms as time and stability allow. If we were to visit such a world in our imagination, we might begin deep below its surface, where a subterranean ocean laps against rocky shores, lit only by the faint glow of mineral-rich vents. Within these waters, life might take the form of translucent beings, bodies adapted to high pressure and complete absence of light. They might resemble ghostly ribbons of tissue, drifting in the currents and feeding on chemical traces. Others might be hard-shelled, crawling across rocky outcrops, armored against the weight of water above. Where heat seeps steadily into the ocean, communities might cluster like oases, each shaped by the particular chemistry of that place. The creatures here would not be hurried. Their metabolisms could be slow, conserving energy in a world where resources are precious. And yet, life could be found not only in the oceans. If a rogue planet retains a dense atmosphere, it could become host to life suspended in the skies, much as microscopic organisms on Earth float through clouds and drift upon winds. In the heavy air of a hydrogen-rich shroud, microbial forms might gather energy by exploiting chemical reactions within droplets or particles. Perhaps they would develop buoyant structures, allowing them to hover within layers of the atmosphere where temperatures and pressures are most favorable. Just as Earth's air holds invisible populations of life we seldom think about, so too might the skies of a rogue planet conceal tiny drifting ecosystems, carried endlessly by sluggish winds under the cover of perpetual night. The forms of such life would likely be exotic to us, bearing little resemblance to the plants and animals familiar in the sunlight world. They may not grow green, for chlorophyll and photosynthesis would serve no purpose in darkness. Instead, they could be pale or translucent, their bodies reflecting their unseen environment. Some might jet glow faintly, producing their own bioluminescence to signal, to lure, or simply to manage chemical reactions. On Earth, countless organisms, from deep-sea fish to plankton, use bioluminescence in ingenious ways. It seems natural to imagine that in an eternal night, such light would become a primary tool of survival, communication, and attraction. Whole ecosystems might flicker gently with living glow, a hidden aurora woven not by stars, but by life itself. The question of energy remains central, for without energy, no life can persist. On a rogue planet, energy might be drawn from the slow release of geothermal heat, from chemical disequilibria in the atmosphere and ocean, or from the interaction of minerals and water. Imagine life forms that feed not on sunlight, but on hydrogen, methane, or sulfur compounds, metabolizing these substances in ways unfamiliar to us. Such metabolisms already exist in the most extreme corners of Earth, where microbes breathe iron or consume sulfur in complete absence of oxygen. On a rogue planet, these strategies might not be exotic outliers, but the very foundation of ecosystems, shaping the nature of life from the smallest microbe to the largest predator. Predators, too, could emerge, though their forms would be strange to our eyes. Without light to guide them, they might hunt through vibrations, sensing the faint disturbances of water or air made by their prey. Their bodies could be elongated and flexible, designed to glide silently through dense liquid, or compact and armored to withstand sudden pressures. Their movements might be slow, conserving every measure of energy, yet their patience would make them deadly in their quiet world. Entire food webs could exist without a single ray of sunlight, each level building upon the chemical energy ultimately released by the planet's interior. It is also worth considering how intelligence itself might evolve in such conditions. Intelligence is not bound to light. It is bound to survival, adaptation, and the need to navigate complex environments. If life on rogue planets had time, millions or even billions of years, it is possible that creatures of perception and awareness might emerge. Their ways of understanding the world would be alien to us, shaped by senses that do not depend on vision. Perhaps they would read their surroundings through pressure waves, much like bats use echolocation, but in denser, darker conditions. Perhaps they would communicate chemically, releasing intricate blends of molecules into water or air, carrying meaning as rich as words. In such an environment, thought itself would be a different kind of light, a beacon shining not outward but inward, illuminating minds that dream without stars. As we let these possibilities unfold gently in our minds, it is important to remember that speculation of this kind is not merely fantasy. It is an extension of science, guided by the lessons of extremophiles here on Earth and by the physics of rogue planets themselves. The universe continually teaches us that what seems impossible often proves merely uncommon, and that life has a resilience beyond what we once imagined. The discovery of microbes living in boiling pools, in acidic lakes, in radiation-blasted environments, or in solid rock has forced us to widen our definition of habitability. Each such discovery whispers that life might find a way in places we once dismissed as barren. Rogue planets, then, may not be empty wanderers but cradles of hidden biology, carrying their own quiet ecosystems in silence across the stars. And yet there is also a deep poetry in this thought. Life in perpetual night would not measure its days as we do, would not rise with the sun, or sleep beneath its setting ice. It would live in rhythms dictated by heat from the core, by chemical tides, by slow cycles of pressure and flow. It would not dream of light, for it would never know such a thing existed. For these creatures, the darkness would not be absence, but fullness, not void, but home. Their bioluminescence might not be seen as a substitute for sunlight, but as their own natural expression, the language of their world. In their silence and shadow, they would live complete lives, unaware of stars above, just as countless beings on Earth live unaware of galaxies beyond. In contemplating them, we are reminded of the vastness of possibility and of how small our own experience is in comparison. It humbles us to think that while we marvel at the sun, while we bask in its warmth and light, other beings may thrive without ever knowing it. It softens our perspective, showing us that life is not confined to one recipe, one pattern, one fragile balance of light and air. It is, instead, a phenomenon of resilience and creativity, willing to shape itself in harmony with whatever environment the universe provides. And so, as our thoughts drift gently toward rest, the possibility of exotic life in perpetual night settles in our imagination like a lullaby. We picture glowing creatures drifting through oceans of darkness, clouds of microorganisms floating in thick atmospheres, silent hunters gliding in pressure-filled seas, and perhaps even minds perceiving the world in ways we cannot fathom. All of them are reminders that life, in its many forms, is not limited to the sunlight we know. It is a cosmic traveler, always searching for a foothold, always ready to bloom in hidden corners. And if rogue planets indeed carry such life across the galaxy, then the universe is far richer, far stranger, and far more wondrous than we could ever fully dream. Let us continue drifting gently along the quiet current of this great exploration, carrying with us the thoughts of strange and hidden ecosystems that might flourish upon wandering worlds. We have already let our minds wander through oceans in perpetual darkness, through dense blankets of atmosphere that preserve warmth, and through the soft imaginings of exotic life shaped without sunlight. Yet, as we dream of what may lie far beyond the reach of our telescopes, we are brought back to the anchor of our own world. For it is here, upon Earth, that the first and most compelling lessons of possibility are found. The creatures we call extremophiles, those who thrive in the harshest corners of our planet, serve as guides, illuminating how life might endure in places where we once thought nothing could survive. To reflect upon them is to build a bridge between what is known and what might be, and in their quiet persistence we find clues to the mysteries of rogue planets and the wider universe. If one were to walk across the familiar landscapes of Earth, from forests to meadows, from rivers to coasts, it would be easy to assume that life demands mildness. Plants and animals flourish where temperatures are comfortable, where water is abundant, and where the air is gentle. It seems almost self-evident that these conditions define the boundaries of habitability, but as scientists have pushed beyond the ordinary, peering into hidden caves, drilling into the crust, diving to the ocean's floor, and venturing into deserts of ice and fire, they have discovered an extraordinary truth. Life has not only adapted to the extremes, it has made them its home. Consider for a moment the boiling hot springs of Yellowstone in the United States, where the water shimmers in impossible colors, brilliant blues and fiery oranges. These colors are not mere reflections of minerals, but the work of living organisms. Thermophiles, heat-loving microbes, thrive in temperatures that would cook most life within seconds. Some live comfortably at 80 degrees Celsius or more, their enzymes fine-tuned to remain stable, where ours would fall apart. They transform chemical energy into sustenance, creating thriving microbial mats that ripple with color in the scalding pools. For these beings, what is deadly to us is not an obstacle but a necessity, a condition that defines the very fabric of their existence. If such life can adapt to extremes of heat here on Earth, might not other forms adapt to the geothermal warmth of a rogue planet, where volcanic activity and hidden vents provide the only source of energy? From the heat of springs, we move to the crushing depths of the oceans. Beneath kilometers of water, where pressure mounts to hundreds of times what we feel at the surface, live the piezophiles, pressure-loving organisms. To us, such an environment would mean collapse, the weight of water crushing bone and organ alike. Yet for microbes and even complex creatures of the deep sea, this pressure is not destruction, but stability. Their membranes, their proteins, their very structures are designed for such conditions, and without pressure they cannot survive. Tube worms, ghostly white and adorned with blood-red plumes, cluster around hydrothermal vents, their bodies nourished by symbiotic bacteria that feast on sulfur compounds. Shrimp with translucent shells crowd in great swarms, finding warmth and sustenance where black smoke rises from the seafloor. In these dark oases, we see a reflection of what might exist in the oceans of a rogue planet, shielded from the vacuum of space by a thick crust and sustained by chemical reactions deep below. Extremophiles also inhabit the frozen corners of Earth, reminding us that cold, too, is not an insurmountable barrier. Psychrophiles flourish in the icy realms of Antarctica and the Arctic, in permafrost that remains frozen year-round, and in glaciers that slowly grind across stone. They survive in conditions where liquid water is scarce, where chemical reactions slow to a crawl, and where energy is limited. Yet their metabolisms tick on patiently, their cells equipped with antifreeze-like proteins that prevent ice from shredding their delicate structures. In the hidden depths of Lake Vostok, sealed beneath 4 kilometers of Antarctic ice, microbial life has persisted for perhaps millions of years, isolated from the surface and thriving in conditions that mimic what we might find beneath the frozen crust of rogue planets or icy moons. Their presence whispers that even in the deepest freeze, where the sun's warmth never penetrates, life can adapt and endure. There are also creatures that endure extremes of dryness, those known as xerophiles. In deserts where water scarcely falls, where the soil lies parched and cracked beneath an unrelenting sky, microbes linger in the tiniest films of moisture, clinging to rock surfaces and subsisting on dew or trace humidity. Their patience is profound. They may wait years for a single rainfall, and yet their cellular machinery remains intact, poised for the moment when water returns. On rogue planets, where liquid water may be rare and fleeting, such strategies could be the difference between extinction and persistence. Life there might linger in dormancy, waiting for cycles of geothermal activity to create temporary warmth, or for chemical gradients to shift in favorable ways. And then there are the acidophiles and alkaliphiles, organisms that thrive in extremes of pH. In sulfuric pools that would dissolve our skin in moments, ACG. Idophiles flourish, their proteins stabilized against corrosion. In soda lakes rich in alkaline salts, alkaliphiles thrive, their enzymes tuned for conditions that would break down the molecules of ordinary life. These beings remind us that what seems hostile to us is not hostile by nature, but only by comparison to our own fragile design. In the atmospheres of rogue planets, where gases might create highly acidic or alkaline conditions, life could adapt along similar lines, finding balance in chemistries utterly foreign to our own, but perfectly natural for them. Some extremophiles endure not only one hardship, but many. The tiny tardigrade, affectionately known as the water bear, is perhaps the most famous. These minute creatures, no larger than the width of a pin, can survive desiccation, radiation, freezing, boiling, and even the vacuum of space. When conditions become too harsh, they curl into a state of suspended animation called a tun, their metabolism slowing to near zero. In this form, they can endure for decades until conditions improve, at which point they revive and resume their quiet grazing on algae and lichens. If life were to spread to rogue planets, whether through natural panspermia or by accident of cosmic collision, creatures like tardigrades remind us that survival across interstellar gulfs is not impossible. They are emissaries of resilience, proof that life can endure almost anything if given the chance. The study of extremophiles has transformed our understanding of habitability. Once scientists thought life was fragile, confined to a narrow range of conditions. Now, they speak of habitability not as a rigid box, but as a spectrum, with life stretching to fill spaces far beyond what we imagined. Each discovery of microbes in harsher and harsher conditions widens the window, pushing back the borders of the possible. It is as though an Earth herself is training us to imagine, to prepare our minds for what we may one day find on other worlds. In this way, extremophiles illuminate the unknown, casting a soft glow upon the path ahead. They teach us that energy can be drawn from many sources, not only the sun. They show us that water, in whatever form, can host communities that endure. They demonstrate that the boundaries we once thought inviolate are merely conveniences of our perspective, not rules of the cosmos. And perhaps most importantly, they whisper that life is not an accident confined to Earth, but a principle of nature, ready to emerge wherever conditions allow, however strange those conditions may seem to us. As we let these thoughts drift gently through our minds, the connection between Earth's extremophiles and the possibility of life on rogue planets becomes clear. The microbes and boiling springs tell us that geothermal heat can sustain ecosystems. The creatures of the deep sea show us that darkness is not emptiness, that life can build entire worlds upon chemical energy. The microbes in ice remind us that cold is not the end, but simply another condition to which life may adapt. The tardigrade tells us that survival is possible even in the vacuum of space. Each of these beings is a guide, each a lantern carried through the darkness, illuminating the path to understanding worlds that we have never seen. And so, as we imagine the endless drift of rogue planets, across the stars, we carry with us the quiet certainty that life may indeed dwell there, waiting in hidden oceans or dense skies. The extremophiles of Earth have shown us the way, their very existence a testament to resilience and adaptation. They are the proof that life does not ask for comfort, only for opportunity. And in that truth lies a gentle reassurance, one that comforts us as we drift toward rest. That the universe may be filled with life, diverse and unexpected, thriving in places we once thought impossible. In the stillness of the night, when thoughts wander easily and curiosity becomes a gentle companion, it is comforting to drift into the story of how humanity seeks to find what cannot be seen. In our journey through the hidden lives of rogue planets, we have touched on their origins, the heat they carry without suns, the oceans they may cradle beneath ice, and the mysterious ways life might endure in darkness. Now, we pause to consider the human endeavor to uncover these worlds, not through direct sight, for they are too faint and cold to shine like stars, but through the subtle signatures they leave behind, whispers in the vast silence of space that reveal their presence. This is the story of technology and theories, of how scientists reach for the invisible, slowly, patiently, and with wonder guiding every step. Rogue planets drift far from starlight, their surfaces shrouded in darkness so complete that even the most powerful telescopes cannot easily find them. Unlike stars, they do not blaze with light. And unlike planets tethered to stars, they do not betray themselves by tugging visibly on the bodies they orbit. Instead, they float alone, black against black, almost indistinguishable from the void itself. And yet, our instruments and imaginations are not deterred. Scientists have devised methods as delicate as listening for a whisper in a storm, ways of discerning the undetectable. It is a slow art, one that blends mathematics, physics, and a steady faith that the universe will reveal its secrets to those who pay careful attention. One of the ways rogue planets are discovered is through a phenomenon called gravitational microlensing. It is a subtle effect predicted by Einstein's theory of general relativity, which tells us that mass bends space itself. When a rogue planet drifts between us and a distant star, the light from that star bends around the planet's G, gravity. For a brief passing moment, the star appears to brighten, not because it has changed, but because the rogue planet has become a lens, magnifying its glow. The effect is temporary, lasting only as long as the alignment holds, and it requires careful monitoring of countless stars to notice such fleeting flickers. But scientists have learned to watch, to let machines stare at the sky without rest, collecting data night after night. Through these blinks of light, whole new populations of unseen worlds have been revealed, like shadows caught only when they momentarily cross a beam of light. The beauty of microlensing lies in its impartiality. It can reveal planets of all sizes, from the giants as large as Jupiter to smaller bodies comparable to Earth. In fact, through these methods, astronomers have suggested that rogue planets may be far more common than stars themselves, drifting by the billions through the galaxy. This discovery is not made with fanfare or sudden flashes of brilliance, but with the slow accumulation of evidence, each flicker of starlight adding to a quiet, growing chorus that tells us of the unseen world surrounding us. Beyond microlensing, scientists have turned to infrared surveys to search for the faint warmth of these cold travelers. Even without the light of a sun, rogue planets may radiate the heat left from their birth or from the decay of elements deep within. Sensitive instruments aboard space telescopes scan the sky in infrared, detecting glimmers that human eyes cannot see. The Wide-Field Infrared Survey Explorer, known as WISE, has already hinted at the presence of wandering worlds, some with masses between those of planets and brown dwarfs, the failed stars that glow faintly in their loneliness. These searches are like feeling for the warmth of a hand in a darkened room, delicate, requiring patience and precision, but deeply rewarding when faint signals emerge. Theories and simulations also play a vital role, because for every observation, there are countless unknowns. Astronomers build models of how planets are ejected from their star systems, how many survive the chaos of early formation, and how they wander afterward. These simulations run on supercomputers, recreating cosmic histories in digital form, testing possibilities against what little data we have. They allow us to ask questions we cannot yet answer through sight alone. How many rogue planets drift within the Milky Way, how often they encounter one another, whether they might carry moons, and what fates await them as they traverse the cold expanse. In parallel, new instruments are being designed to push the boundaries of what is possible. The Vera C. Rubin Observatory, with its wide, deep view of the sky, will begin a survey capable of catching transient events like microlensing with greater detail than ever before. Future space telescopes, such as the Nancy Grace Roman Space Telescope, are expected to revolutionize our knowledge of rogue planets, providing a wealth of data that could confirm whether they truly outnumber the stars. Each new telescope is like a new set of eyes, more sensitive, more discerning, able to capture whispers that were once beyond hearing. There is also the tantalizing possibility of finding not just rogue planets themselves, but evidence of the environments they harbor. Some theories suggest that rogue planets with thick atmospheres may trap heat, emitting faint signals that could, with advanced technology, be distinguished from the background of space. Others imagine that moons orbiting rogue planets could betray their presence through subtle gravitational wobbles or the dimmest traces of reflected light. None of this is simple, and most of it is still in the realm of speculation, but speculation in science is not idle. It guides the direction of observation, shaping the designs of instruments and the focus of surveys. What is perhaps most remarkable is the persistence of the human spirit in this search. To look for rogue planets is to admit that much of what exists is hidden from view, that the universe is not only vast, but veiled, and yet we are willing to reach into that veil. The endeavor requires humility, for we know we may never find all that is out there, but also hope, for even small discoveries remind us that the cosmos is richer and stranger than we imagined. It is a pursuit that blends the rigor of equations with the wonder of curiosity, carried out in laboratories and observatories, but inspired by something deeply human, the desire to know where we are and what shares this galaxy with us. The search for the invisible also raises philosophical reflections. In seeking worlds that cannot be seen, we confront the idea that absence of evidence is not evidence of absence. Just because something is hidden does not mean it does not exist. The universe, in its immensity, contains more than what our eyes can perceive. And so, when scientists spend years chasing the fleeting brightening of a star or the faintest warmth in infrared, they are not only collecting data, they are affirming a belief that the universe is knowable, that patient attention can bring the invisible into the realm of the known. The journey into this hidden realm is still in its early stages. Much of what we imagine about rogue planets remains hypothetical, supported by fragments of evidence and models that may shift as new discoveries are made. But even in this uncertainty, there is a deep calm, a sense of being part of a slow unfolding. Just as the planets themselves drift quietly, scientists too move patiently, allowing time, observation, and innovation to reveal what lies beyond. As we rest with these thoughts, the mind can wander to the gentle image of countless worlds floating silently through the dark. Most unknown, many unseen, yet each with a story to tell. Some may carry heat deep within, others oceans beneath ice, and perhaps a few cradle life in forms we have yet to imagine. They are out there, and though we cannot yet see them clearly, we have begun to listen, to feel, to trace their presence in the faintest of signs. In this quiet pursuit, science and wonder walk together, not hurriedly, but at a calm pace, keeping company with the drifting planets themselves. And so, in the stillness of night, as the stars shine steadily above, we can close our eyes with the thought that the universe is larger and more mysterious than we can see, yet not beyond our reach. With time, patience, and imagination, the invisible becomes visible, the unknown becomes familiar, and the endless darkness becomes just another place where secrets wait to be gently uncovered. Across the journey we have taken so far, we have wandered among lonely planets drifting far from stars, felt the secret warmth they may hold deep within their hearts, listened to the whisper of hidden oceans and vents that breathe heat into the darkness, and marveled at how science strives to find what cannot be seen. We have lingered on the fragile possibility of life in places where no sunlight shines, drawing comfort from the knowledge that even in the most extreme corners of our own Earth, life has managed to survive. Now, as the story unfolds further, another thought begins to rise softly, as though carried on the still air of a quiet night. What if these wandering planets are not merely silent travelers, but vessels, cosmic arks that carry the ingredients of life, or even life itself, across the vastness of the galaxy? It is a thought that seems at once bold and gentle, daring and contemplative. For when we imagine planets cut loose from the embrace of their stars, we often think of them as forsaken, barren, or doomed to eternal exile. Yet perhaps exile is not the right word. Perhaps, instead, these worlds are voyagers, set adrift on journeys longer than any star-bound planet could ever know, drifting not in despair but in quiet purpose, bearing the seeds of life through the void. The idea that life might travel across the cosmos is not new. For more than a century, scientists and dreamers alike have entertained the concept of panspermia, the possibility that life does not always originate in isolation, but may be spread, carried from one place to another by comets, asteroids, or dust. Microbes, hardy and resilient, can survive the cold of space, shielded within rock or ice, slumbering for eons until they find a home where conditions are right once again. But if tiny fragments of rock can serve as messengers of life, how much more could a whole planet accomplish? A rogue planet, with its gravity, its protective layers, its hidden warmth, could provide a shelter far more hospitable than a bare shard of stone. In this way, such planets could become true arks, preserving and transporting the fragile flame of life across interstellar distances. Imagine, for a moment, a planet cast out from its star system, hurled into the darkness by the chaos of early formation. On its surface, ice forms quickly, an armor against the cold. Beneath that frozen shell, however, warmth from within endures. A subterranean ocean churns, kept liquid by the planet's own heat, by radioactive decay or tidal stresses if moons still orbit it. Within that ocean, chemistry unfolds much as it once did on Earth, driven by vents and minerals, giving rise to molecules that bind and spiral, seeking ever more complex forms. Over millions of years, something stirs, perhaps not identical to life as we know it, but still alive, still capable of feeding, reproducing, adapting. Life begins not under the light of a sun, but in the solitude of a drifting ark. As the planet drifts, ages pass like breaths of the cosmos. It moves silently between the stars, untouched by radiation that might scorch it, undisturbed by the turbulence of orbits around a blazing sun. In its darkness, life evolves at its own pace, cocooned, patient. Should the ark one day pass near another star system, its frozen exterior may shed fragments, comets born from its ice, carrying within them tiny passengers from the hidden sea. These fragments might fall into the pull of another star, striking young planets where conditions are ripe, seeding them with possibilities. Thus, life that began in the shadows of one rogue planet could awaken under the skies of another world, far across the galaxy. This vision is both scientific speculation and gentle poetry, yet it is not entirely fantasy. On Earth, we know that certain microorganisms are astonishingly resilient. Some can withstand freezing for thousands of years, revived when thawed. Others survive high doses of radiation or the crushing pressures of the deep ocean. There are bacteria that endure the vacuum of space itself, tested on the exterior of spacecraft, clinging to life even after months without protection. If such creatures exist here, born of Earth's fragile biosphere, then how much more could evolution produce on worlds where survival in darkness is the only path forward? On a rogue planet, life would not merely endure, but specialize, adapting to the peculiar rhythms of a world without a sun, preparing, perhaps unknowingly, to one day journey beyond. Rogue planets as arks offer another perspective as well. Perhaps some of them do not begin life entirely anew, but instead capture it from elsewhere. Imagine a star system rich with comets and asteroids, debris carrying the early chemistry of life. A massive planet, later ejected into interstellar space, gathers this material during its youth, storing it away in oceans or beneath protective crusts. Then, as it drifts through the galaxy, it keeps that material safe, shielding it against cosmic rays, holding it through epochs so long that entire civilizations might rise and fall on other worlds before the ark delivers its gift. One day, a fragment escapes, or the planet itself is captured by a new star system, orbiting once more and spilling its hidden contents into fresh environments. Life spreads, not explosively, but gently, like seeds scattered on a breeze that spans the stars. The question, of course, is not only could this happen, but has it happened? When we look at Earth and wonder about the origins of life here, we do not know for certain Wetbab. Her life began in our own oceans, or arrived from elsewhere. Some theories suggest comets and asteroids may have brought the building blocks, molecules essential to biology. If this is true, then rogue planets could be the grandest couriers of all, transporting not just molecules but ecosystems, not just seeds but entire gardens of potential, preserved in isolation until chance brings them into contact with fertile ground. The notion of planets as cosmic arks also changes how we think about our place in the galaxy. If life can spread in this way, then we may not be as alone as the darkness sometimes makes us feel. Every drifting planet might be a cradle, holding within it stories of evolution unfolding unseen, waiting for a moment of connection. Perhaps our galaxy is not a sparse landscape of rare life, but a garden where the gardeners are invisible, traveling slowly, silently, carrying their charges through endless night. In this sense, the search for rogue planets becomes even more profound. We are not merely cataloging wanderers, we may be glimpsing the carriers of life's greatest journeys. Each discovery hints at possibilities, Could that world hold oceans? Could those oceans harbor microbes? Could fragments of those microbes already be scattered somewhere ahead in their path, waiting to be caught by a young, habitable world? The story unfolds not as certainty, but as possibility woven into the fabric of time and space, an endless tapestry in which every thread is a drifting world, every knot a new chance for life. Technology will one day allow us to probe more deeply, perhaps even to detect biosignatures on such planets if their atmospheres are thick enough, or to sense chemical imbalances that suggest something stirring within. For now, we dream and speculate, guided by what we know of Earth and its extremophiles, by what we understand of physics and chemistry, and by the patience of science that looks not only at what is, but at what could be. And as we think of these drifting arks, there is also a philosophical comfort. Life, fragile as it is, seems determined to endure. It clings to vents in the deep sea, to frozen soils, to clouds high in the atmosphere. It persists in deserts and caves, in acid and ice. If life can survive in all these places, why not on the great ships of stone and ice that sail between stars? If life can endure there, then perhaps its destiny is not confined to a single world, or even a single system, but stretched across the galaxy, scattering, surviving, and beginning anew. As we drift towards sleep, we can let our minds settle on the quiet vision of countless rogue planets, each one dark, each one silent, and yet inside, perhaps, carrying something bright and vital. They move slowly, crossing gulfs of space we can barely comprehend. But their journeys are not wasted. They are like lanterns hidden under thick cloaks, their glow unseen but never extinguished, traveling until the day comes when they may share their light once more. To imagine rogue planets as cosmic arks is to imagine the galaxy itself as alive with potential, its silence not empty, but full of quiet travelers carrying ancient cargo. It is to imagine that even when we cannot see it, life may be moving, spreading, and enduring in ways that defy our limitations. And it is to rest in the thought that somewhere, perhaps far away, life is stirring right now within a hidden ocean beneath an endless night, waiting to be carried into tomorrow. The story of rogue planets, those drifting worlds cast adrift from the warmth of their stars, has carried us through many places already. We have imagined their births in the chaos of young systems, followed them into exile across the dark gulfs of interstellar space, peered into the hidden reservoirs of warmth that glow faintly within their hearts, and wondered at the oceans they may shelter beneath their icy shells. We have lingered over vents that breathe life in the absence of sunlight, pictured thick atmospheres wrapping themselves around lonely worlds to hold in precious heat, and dared to envision exotic forms of life evolving in perpetual night. We have even entertained the thought of these worlds as cosmic arks, carrying seeds of existence across the galaxy, dispersing the miracle of biology into places far beyond our sight. But now, having walked this path, a quieter, more contemplative question waits for us, soft as the hush that settles at the edge of sleep. What does it mean for us as human beings if life can exist without light? What does such a possibility tell us about life, about existence, and about ourselves? It is a question not of machinery or measurements, but of perspective and wonder. For as long as humans have looked at the sky, light has been our measure of reality. We rise with the sun, we mark the passing of days by its arc, and our very sense of time and rhythm is tied to its glow. Light feeds the plants that nourish us, warms our skin, and reveals the world around us in color and clarity. In myth and story, light has always symbolized creation, knowledge, and hope, while darkness has often been cast as the place of unknowing, of fear, or of endings. It seems almost natural to assume that without light, there can be no life, no meaning, no continuation. And yet, the universe offers us another lesson. It whispers that life does not always need the light, that it may find its way in places where no dawn ever comes, and that existence may be full even in the heart of eternal shadow. This idea gently loosens the bonds of our assumptions. We imagine creatures that have never seen the day, never known what it means to be warmed by a star. Their world is not shaped by the rhythm of light and darkness, but by other signals, by vibrations moving through water, by chemical trails drifting in currents, by heat rising in the invisible. For them, there is no absence, because there is no expectation of light. What to us feels like deprivation, to them would be normality, the very definition of existence. their lives would be no less whole, no less rich, for lacking what we hold so dear. And in realizing this, we too are changed, for we begin to understand that our way is not the only way, that the story of life is wider and more varied than our own chapter in it. We see shadows of this truth even here on Earth. In the lightless depths of oceans, far below the reach of the sun, entire ecosystems thrive around hydrothermal vents, each community woven together not by sunlight, but by chemistry. Bacteria harness energy from the minerals rising from Earth's interior, and upon them are built networks of worms, crabs, fish, and other beings, none of which have ever seen the sun. Their existence is a quiet affirmation that light is not the sole source of vitality. Darkness, too, can be fertile. In caves sealed from the surface, in rocks buried deep underground, in icy pockets beneath glaciers, life endures without ever knowing the sky. These examples show us that our view of what is necessary is narrow, that life can flourish under conditions we might once have dismissed as impossible. The philosophical wonder of life without light rests partly in this widening of perspective. It shows us that existence does not depend on our expectations. To live is to find a way, even when familiar supports are absent. In the same way, perhaps we too can draw comfort from this truth. When we find ourselves in times of uncertainty, when clarity is missing and answers are obscured, we can remember that life itself often thrives in darkness. The absence of light is not the end of meaning. It can be the ground of new beginnings, of different forms of endurance, of quiet but persistent becoming. There is also something humbling in the recognition that our experience is not universal. We so often assume that light is central because it is central to us, but for other forms of life, it may be irrelevant, and yet their lives are no less real. This realization invites us to loosen our hold on the idea that our way of knowing and experiencing is the only valid one. It encourages a humility that is gentle, not diminishing, reminding us that the universe is larger than we are, and that within it, there are endless ways of being. In the dark oceans of rogue planets, creatures may dwell who would never understand our attachment to light, just as we cannot fully grasp their ways of sensing. Yet in both, life unfolds, and in both, existence is meaningful. When we allow this thought to sink in, it becomes a kind of meditation. We picture the galaxy not as a theater lit only by its countless stars, but as a vast sea where islands of darkness float, hidden and silent, yet alive. Some carry oceans sealed beneath ice, others wrap themselves in thick, insulating air, and still others carry warmth in their cores. In those places, beings may move and feed, reproduce and evolve, without ever looking up into a sky, without ever wondering what lies beyond. Their world is entire, complete. They do not live in lack. They live in fullness, but a fullness unlike our own. To rest with this image is to feel a widening of possibility, a loosening of the boundaries we draw around the meaning of life. In this sense, the existence of life without light reshapes not only our science, but our philosophy. It tells us that life is not fragile in the way we once thought. It is adaptable, resilient, able to find a foothold where none seems to exist. It can make a home in conditions far from those we consider normal. This adaptability speaks to an underlying principle, that life is not a narrow accident, but a tendency of the universe, a way that matter organizes itself into persistence. To think this way is to feel a quiet reassurance, as though the cosmos itself leans toward vitality, toward growth, toward endurance. It makes us wonder if perhaps life is not rare but inevitable, not confined to light but spread through shadow, waiting wherever it can. There is, too, a more intimate lesson for us. We often associate light with knowledge, with clarity, with truth. To live in darkness feels like ignorance, like stumbling without direction. But if life can thrive in darkness, then perhaps meaning too can exist without total clarity. Perhaps it is not always necessary to see everything in order to live fully. Just as creatures on rogue planets might navigate by heat or chemistry, we too can find our way by signals subtler than certainty. We can dwell in mystery without being lost. We can live without always knowing, and still live meaningfully. As this thought settles, it becomes easier to rest. The universe, it seems, is not bound to our comforts, and yet it offers comfort in return. The drifting planets, cloaked in silence, may harbor more vitality than we dare expect. They remind us that life is not limited to what is visible, that the unseen is not the unreal, and that the absence of light is not the absence of possibility. They teach us that meaning can be found not only in brightness, but in shadow, not only in clarity, but in mystery. As we drift deeper into this reflection, it becomes a kind of lullaby, a gentle rhythm that reassures rather than unsettles. The thought of life without light no longer feels alien or frightening. It feels expansive, inclusive, part of a universe that is endlessly generous in its possibilities. Just as the stars shine in their brilliance, so too may the darkness cradle its own wonders, unseen but present, silent but alive. In the quiet of the night, as we close our eyes and let the images soften, we may picture once again those rogue planets sailing through the galaxy. To our instruments, they are dark. To our eyes, they are invisible, but within them, there may be seas, vents, and forms of life that never knew the sun. They drift not in emptiness, but in wholeness, carrying their own meaning, their own beauty, their own truth. And in thinking of them, we too find peace, for they show us that existence is broader than we can imagine, and that even in the absence of light, life finds a way to shine. As we let our thoughts linger on the philosophical wonder of what it means for life to exist without light, the natural step forward is to wonder not only about what has already been revealed to us, but about what lies still ahead. The journey of imagination and discovery is never truly finished, for each answer the universe grants us only opens a doorway to further mysteries. The story of rogue planets, subterranean oceans, strange chemistries, and the idea of life unfolding in places we once believed barren, all of these have carried us to the edges of what is known. Now we stand in a place of anticipation, peering quietly into the expanse of possibility, asking ourselves what discoveries await, and how our own expanding imagination may shape the path we take. For so long, humanity's understanding of the cosmos was tethered tightly to the visible. We learned to map the stars, to track their motions, to tell stories about their patterns. Light was our guide, the only messenger across the great distances. Yet, as we have seen, life does not always depend on light, and neither does discovery. Our instruments have grown more subtle, more attuned to whispers beyond the visible, more capable of detecting signals that lie beneath the surface. Infrared telescopes peer into dust-shrouded nurseries where stars are born. Sensitive radio arrays listen for the faintest pulses and murmurs from deep space. Even the slight dimming of a star can reveal the presence of a planet crossing in front of it, and the tiniest tug on a star's motion can betray the hidden gravity of an unseen companion. Through these delicate methods, we have already discovered thousands of planets orbiting other suns, and in their variety, we glimpse the promise of countless more. But rogue planets, those that wander free, unbound by any star, remain elusive, glimpsed only in the faintest hints. Their darkness hides them, their silence conceals them, and yet we know they must be numerous. Some estimates suggest there may be more of them than there are stars. Each one is a world in itself, perhaps carrying oceans, perhaps carrying warmth, perhaps even carrying life. To think of them is to sense a quiet richness scattered through the galaxy, like seeds drifting on unseen currents. And the thought of discovering them more fully draws us onward, urging us to refine our tools, to expand our reach, to imagine new ways of seeing what cannot be seen. The future of discovery, then, is a story not only of technology, but of imagination. For every instrument we build begins first as an idea, a vision of what might be possible. We imagine what it would mean to listen more closely, to see more faintly, to measure with more precision, and then we work patiently toward making that vision real. In the centuries past, it was unimaginable that we could detect planets around distant suns. Today it is routine. What seems impossible now, perhaps the mapping of subsurface oceans on planets dozens of light years away, or the detection of chemical signs of life in the atmosphere of a free-floating world, may one day be as familiar to us as the sight of the moon in the sky. There is something soothing in this realization, for it tells us that discovery is not a single leap, but a slow unfolding. Each generation reaches a little further, adding its own threads to the tapestry. Just as the creatures we imagined living without light find their way by other signals, so too do we move forward by sensing what is faint and uncertain, by allowing imagination to guide us where certainty cannot. The pace may be gradual, but the direction is clear. Outward, onward, ever deeper into the unknown. And what of imagination itself? It is more than a tool for science. It is the very heart of how we connect with the universe. When we imagine life on rogue planets or envision creatures evolving in perpetual night, we are not only entertaining possibilities, we are practicing empathy for the unfamiliar, stretching the boundaries of what we consider meaningful, preparing ourselves for surprises the universe may one day reveal. This expansion of imagination is itself a discovery, one that changes us as surely as new data changes our models. It makes us larger within, more capable of holding wonder, more attuned to the quiet truth that existence is greater than any single perspective. Looking ahead, we can dream of missions that may one day set out to explore the wandering worlds. Perhaps spacecraft, equipped with instruments sensitive enough to detect the heat signatures of rogue planets, will map their distribution across the galaxy. Perhaps probes, powered by new forms of propulsion, will fly closer to these worlds, skimming their atmospheres, peering through their icy shells, searching for the chemical fingerprints of life. Perhaps even further into the future, humanity itself, or the beings we one day become, may set foot on these dark planets, carving out homes in their hidden seas, lighting them with our own radiance. Such thoughts, though distant, carry a gentle reassurance. They remind us that possibility is not a fixed boundary, but a horizon that recedes as we walk toward it. The discoveries to come will not only reshape our understanding of the universe, they will reshape our understanding of ourselves. To learn that life can exist without light, without stars, without the conditions we have always thought essential, is to learn that life is far more versatile than we imagined. It is to accept that we are not the measure of all things, but one example among many. This realization can humble us, but it can also enrich us. It teaches us that existence is not fragile, but resilient, not narrow, but expansive. It prepares us to meet the unknown, not with fear, but with curiosity, not with dread, but with wonder. And so, when we peer ahead into the future, we do not see an end but a widening path. We see humanity continuing to listen to the silence of space, continuing to build instruments of exquisite sensitivity, continuing to dream of what may lie beyond the next horizon. We see our imagination expanding, not shrinking, as we accept more fully the truth that the universe is full of possibilities. And as we picture these futures, we can allow ourselves to rest in the knowledge that discovery is not only about what we find, but about how we grow in the process. The rogue planets drift on, unseen, carrying their secrets. The stars shine, scattering their light across the cosmos. And we, tiny beings on a small world, gaze outward, wondering, imagining, reaching. Each discovery is like a lantern lit in the darkness, but the darkness itself is not empty. It is fertile, waiting, holding mysteries that will one day become familiar. The future stretches before us, not as a fixed road, but as an open sea, vast and full of currents we have yet to trace. And in that vastness, we find not despair, but comfort. For the unknown is not only a challenge, it is also an invitation. As you drift now toward rest, you might picture the galaxy itself breathing around you, stars like scattered embers, planets moving in silence, rogue worlds drifting with their hidden oceans and unseen life. You might imagine the scientists of the future building ever more delicate instruments, listening ever more closely, their work guided not only by reason, but by wonder. And you might allow yourself to feel part of this ongoing story. A story that stretches from the first creatures who looked at the stars and asked what they meant, to the far-off generations who may one day touch the oceans of worlds we now only dream of. In this way, the future becomes not a source of worry, but a gentle horizon. It is not some thing we must rush toward, but something that will arrive in its own time, just as the next dawn always follows the night. Our role is to keep imagining, to keep wondering, to keep listening. For imagination itself is the bridge between the present and the future, between what is known and what may yet be. And as long as we can imagine, as long as we can dream, we are already part of that unfolding. So let us peer ahead, not with anxious urgency, but with calm curiosity. Let us rest in the thought that the universe is vast, that discovery is endless, and that our imagination will continue to expand as surely as the cosmos itself expands. In the gentle rhythm of this truth, we can find peace. The journey is ongoing, the mysteries are abundant, and the future is open, waiting for us with quiet patience. And as you close your eyes and drift into sleep, you drift also into that great current of discovery, carried softly forward by the endless wonder of what lies ahead.